Hello everyone and welcome to BCN 3D webinars. Today we're going to talk about materials for 3D printing and fiber-filled filaments. My name is Dario Destro and I am material engineer here in BCN 3D. Today we're going to talk about the material properties, all the filaments that we have in our portfolio, and how to choose between one or the other depending on the final application. We're also going to talk about fiber-filled filaments, and also I'm going to talk about an interesting case of an application of fiber-filled filaments for building parts for an electrical racing car. Let's start with fused filament fabrication. That's also called FFF or FDM. It's one of the most known and common 3D printing technology. It's known for being very accessible because you can find machines for a relatively low price, and they're easy to manage and easy to use. Also, the materials are pretty cheap. They're common filaments made of thermoplastics, and these thermoplastics are normally used in the industry. So the industry is already familiar with it, and this is an advantage since once you prototype something and you build it with your 3D printer, you can directly assume that a final part made maybe with a standard technique like injection molding will behave the same way as your 3D printed part. Also, 3D printing with FFF is pretty easy, and someone with not a lot of experience in additive manufacturing in general can start and print straight away just after buying the first spool of filament and printer. Now, here on this graph you can see a list of 3D printing filaments. We have divided our portfolio in 4 different categories. And so we can start from the basic one, which is, for example, PLA, PETG, TPU, PVA. These are filaments that are normally easier to print compared to others, mostly because the melting point of the filament is lower. So these filaments do not need a closed environment for the printing. PLA, PETG are normally used to make prototypes, to build parts, to have a look at the shape, at the colors, before maybe making a part using standard techniques. TPU is an elastomeric material. It's nice. It's good to be used when you want to make something that has to be flexible, that has to be able to stretch. And PVA is interesting because it's a soluble material. It's normally used as a support material for PLA and allows you to 3D print weird, strange geometries you could not print, for example, using standard techniques. Then we have the advanced segment. The advanced segment contains, for example, ABS, polyamide, and polypropylene. These materials are normally called technical materials or engineering plastics. And yes, they have better performances compared to the basic ones. They're normally used for end-use parts, and they can, for example, withstand a heavy use or particularly harsh environments. Finally, we have the Pro series, which in our case is the fiber-filled materials. These materials are filled with fibers which give particular mechanical properties such as strength and stiffness and heat resistance. In the end, we have high performance materials which are normally used in industrial 3D printers. They require very high printing temperatures, and they're not in our portfolio at the moment. Our materials come from MCCP, which is part of Mitsubishi Chemicals, and BASF, which these 2 companies always guarantee an optimal quality of the filament and of the print. Now, let's focus more in detail on the mechanical properties of these materials. We're going to talk about tensile strength, elongation and break, flexural modulus, impact strength, and heat deflection temperature. So let's start from tensile strength, which is the most easy to understand. Tensile strength is the actual strength of the material. And to make you understand it, imagine a bar made of material. It's the strength needed to pull the bar and break it. Then we have elongation at break, which is a similar experiment, but instead of measuring the strength needed to break the bar, we're measuring how much the bar elongates. So, for example, if a material has an elongation at break of 100%, it means that before breaking, you will be able to double its length if you're pulling it. Then we have flexural modulus, which is the index of stiffness of the material. So it's the resistance that the material has to a bending movement. So normally rigid materials, stiff materials have a very high flexural modulus. Then we have impact strength, which is a very important mechanical property, even if sometimes it's a little bit overlooked. This is very important, especially if you want to build an end-use part, something you want to use, you want to put into a machine, something that will be in contact with vibrations, or that would be a chance to, for example, for the part to fall from a table, for example. And finally, we have heat deflection temperature, which is commonly referred to as heat resistance. It's an interesting experiment where you take a bar of your material, you heat it up while applying a weight. So it's not only the thermal resistance of the material, it's the thermal resistance under pressure, under stress. Now, here you can see an interesting graph, which is a nice panoramic view of our filaments. On the left, we have the tensile modulus, which is the stiffness in blue. And on the right, you can see the maximum elongation, which is the flexibility in gray. You can see that on the left, we have very rigid materials. On the left, there is polyamide carbon fiber, polypropylene glass fiber. These materials are very stiff, and obviously, if they're very stiff, they're not very flexible. So their elongation at break will be pretty low. On the right side, instead, we have flexible materials. They will be very little stiff and very flexible. TPU, for example, can be elongated up to 400%. So it means that you can stretch it up to 4 times its original length. And so it's very good for parts that have to behave like a spring or like a gasket. In the middle, we have ABS and polyamide, which are semi-rigid materials. ABS, it's rigid and also is impact resistance, and it's normally used when you want an intermediate type of behavior, something that maintains its shape, that it's rigid, but also can take a hit, if hit with a hammer or if dropped on the floor. Here we have then represented the impact strength of our 3D printing filaments. And this is an interesting graph. It shows you how PLA is much worse compared to other filaments. So PLA is good for prototypes and for example, to study the shape of something you've recently designed, but it's not very good for impact resistance. You probably are familiar with the fact that PLA can break quite easily compared to, for example, ABS. So then we have PETG, which is a better alternative to PLA in terms of impact strength, but it's not comparable to TPU, ABS, and PA, which have the highest impact strength of our portfolio. Filaments like polypropylene and polyamide and polypropylene glass fiber and carbon fiber do not have exceptional impact strength. So for all those applications when there's a chance for the part to be hit or with vibrations, we always suggest using ABS or polyamide or TPU. Then we have the heat resistance. The heat resistance, you can see there's a sort of trend in the graph. PLA has a pretty low heat resistance together with polypropylene. PETG is slightly better. ABS and PA have a sort of intermediate behavior, so they can be actually used if the environment is at 50, 60 degrees without any type of concern. But if you are going to use this final part in a heated environment, or in the presence of the sun, for example, inside on the cockpit of a car, we suggest using polyamide carbon fiber or polypropylene glass fiber, which can resist temperatures as high as 120 degrees. Now, chemical resistance. This is something that not always people talk about in the 3D printing industry, but it's very important, especially if you're 3D printing something that you're going to use effectively. So we are constantly exposed to substances that can be water, soap, or fruit juice. And these parts need to withstand all these agents. So let's start with acids, which are maybe the most famous chemical agents. They're pretty aggressive. And as you can see, PLA, ABS, polyamide, and TPU cannot withstand very well the exposure to acids. But PETG has a decent resistance. Obviously, polypropylene is known for being exceptionally chemically resistant, and as you can see, it basically resists to most of the chemical agents that we've put in the table. Then we have bases. Bases are the opposite of acids. They react with acids, and bases are, 3D printing filaments are slightly more resistant to bases. We can see that PLA is not resistant to bases. PETG, that was quite resistant with acid, is not resistant with bases. ABS and PA and TPU have a decent resistance. Polypropylene, as always, is resistant to bases. Then we have water, which might look like an innocent, harmless substance, but can actually penetrate the polymer network of our 3D printing filaments, even after printing. So not all the filaments are suited to be exposed to a water-rich environment. It doesn't have to be liquid water, it can also be a high humidity environment. So PETG is notoriously resistant to water, and polypropylene as well. Then we have solvents. Concerning solvents, I suggest you visit our webpage. We have a very interesting study where we show the effect that solvents have on our 3D printing filaments. And there you can visually see what happens if you immerse a 3D printed part in a common paint thinner we chose as a solvent. So PLA and ABS simply dissolve in paint thinner and solvents. They can be acetone, a paint thinner, petrol. PETG and PA and TPU have a decent resistance. They do not keep the original shape though. They tend to swell, and so they slowly degrade when in the presence of solvent. Polypropylene is the most resistant one, as always. So this was the first part of the presentation. We've talked about our filaments, how do they behave in different situations, and how to choose between one or the other, depending on the final application. Now we're gonna go more into the details of what are fiber and what are fiber-filled filaments. So fibers are a specific type of filler. And filler are everything that are added into a polymer blend. Normally, historically speaking, fillers were used to decrease the cost of a polymeric material. So you have to imagine during the 50s, polymers were a relatively new material, they were expensive. So people used to add inorganic fillers to reduce the cost of the total blend. But later we discovered that actually adding the correct type of filler in the right amount can greatly improve some of the mechanical and physical properties of the polymer blend. So for example, the thermal resistance, the thermal conductivity, and for example, fillers are known to reduce the thermal, the coefficient of thermal expansion and the flammability. Now, there are many types of filler. We can characterize and classify them depending on the chemical composition. So for example, we have inorganic fillers such as talc and calcium carbonate, for example, or organic fillers such as polymers like Kevlar or particles like carbon. We can also divide the fillers depending on the shape of the particles that compose them. And normally these particles are microscopic or nanoscopic, and they have different shapes. For example, spheres are used to increase the compression resistance of a material because they can withstand stress in all the directions at the same time. Platelets are used, for example, because they generate this layered structure, and they're used to increase the barrier effect, and for example are used to decrease the gas permeability of a polymer. Finally, we have fibers, and broad fibers especially are a special type of filler. Fibers are a sort of approximation of a monodimensional object, so they develop on only one direction, and this is why they increase the mechanical properties, especially on one direction. And they dramatically increase the mechanical properties sometimes. There's two types of fibers. There's the long fibers, which are the ones that are used to weave the carbon fiber sheets that are used to laminate carbon fiber laminate materials. And then there's short fibers, which are the same fibers just cut shorter, normally between 0.1 and 0.5 millimeters, and they're normally used as a filler for thermoplastic materials, and they're the ones that are used for 3D printing filaments as well. So for 3D printing, normally glass fiber and carbon fiber are used. Why? Glass fiber, for example, is the cheapest one to produce and is being historically used for a lot of time. And it increases the flexural resistance, the toughness, and the chemical resistance. Also, glass has an advantage, which is that it's transparent, and it's also an electrical insulator. Carbon, on the other hand, is a little bit more expensive, but it increases dramatically the strength and the stiffness of the polymer material. It's a very light filler, and it increases also the temperature resistance. You have to think that carbon has the highest melting point of all the elements. It's also conductive, and it only has one advantage, which is that it only comes in one color, which is black. So these fibers are normally added to 3D printing filaments to increase the strength and the stiffness, to reduce the thermal contraction and the heat resistance in general. And they also increase the printability of the filament, mostly because of this reduction of the linear coefficient of thermal expansion. And they also give this nice and pleasant matte finish. We have two filaments in our portfolio that have fibers in the blend, which are PAHT-CF15, which stands for polyamide high temperature carbon fiber 15, which has the highest resistance to heat, and it's the strongest and the most stiff material in our portfolio. Then we have polypropylene glass fiber 30, which combines the great chemical resistance and low weight, low density of polypropylene with the strength and the stiffness of the glass fibers. Now, to go more into the details of the mechanical properties, we can do this comparison. We can take one filament without the fiber and its analog filament in our portfolio with fibers. For example, we have here polyamide and polyamide carbon fiber compared for tensile strength, which is the strength necessary to break a bar of material. We can see that just by adding 15% of carbon fiber, the tensile strength was increased from 33 to 62, which is almost the double. The effect is even stronger in the case of polypropylene, which increased from 11.9 to 41.7, almost 4 times more. So this is a good example of the effect of the fibers. Here we have elongation and break. Now, when something becomes more stiff, it will also be less flexible. So you won't be able to extend it as much as you could before. Now we can see that polyamide that had an elongation at break of 143%, just by adding 15% of carbon fiber, that elongation was reduced to 2.9%. So it's a dramatic effect on the flexibility of these materials. For polypropylene, the case is the same. From 200%, the elongation at break went to 4.4%. So again, it's a trade we have to do. When we gain in stiffness, we will also have to take into consideration that we will lose flexibility. Another mechanical property here is the stiffness, which is one of the mechanical properties that fibers are the best at increasing. For polyamide, for example, which is not an especially stiff material, we can see that the stiffness increased from 400 to 6,000, which is almost 15 times more. So from a semi-flexible material, we end up with a super rigid material. For polypropylene, the effect is less pronounced, mainly because glass fibers are a little bit more flexible than carbon fibers, so they do not increase the stiffness that much. Then we have impact strength. Impact strength, polyamide is the best material for impact strength. It has an impact strength of 85.4 kilojoules per square meters, which is uncomparable to the other filaments. So by adding carbon fiber, which are very rigid and stiff, we are obviously reducing the impact strength. So this material is more fragile in the end. So from 85, we end up with 5. In the case of polypropylene, this is not observed because glass fiber increases the impact resistance, and also polypropylene is a more flexible material in general. So we have basically the same impact strength, and this is good. So we can say the polypropylene glass fiber is a good impact resistance alternative to polypropylene. It's just more strong and more stiff. Heat deflection temperature. So this is another property that's improved by the addition of fibers. So in the case of polyamide, we start from a heat deflection temperature, which I remind you is that temperature at which a bar of material starts to bend when you apply a weight. In this case, we're applying 1.82 megapascals, which is a pretty strong pressure. So it's something like 20 kilograms per square centimeter. So we're applying on the bar of the material during the test. So from 65, by adding carbon fiber, we go to 92. So you can say that you can use polyamide carbon fiber in a heated environment up to 90 degrees, even if you're applying a lot of pressure. If you're not applying any pressure, the material is stable, it keeps its shape up to 150 degrees. The case of polypropylene is the same. We have a great improvement of heat deflection temperature. We go from 41 to 73. And so this was the explanation of what are fibers and what are filaments with fibers, and as a description of our filaments in our portfolio and how they behave. Now, I have a very interesting case I want to talk to you about. It's the ETSEIB Motorsport case. It's a very interesting application of 3D printing to a real case. The ETSEIB team is a university team. It participates to Formula Student, and they have built and designed these electric cars, racing cars. And they had this issue. They wanted to design and manufacture different air cooling ducts for brakes. And so they wanted to explore different designs, and they wanted to do it in an agile way. So they thought of 3D printing rightly, and they made good use of 3D printing for this type of application. So these cooling ducts need to cool down the brakes during the race. So depending on the shape of the racing circuit, so on the average speed, on the amount of braking that it's needed, they needed to change the shape of the cooling duct in order to always have the optimal temperature on the brake. So they designed 3 different shapes and they 3D printed them. And it worked well because 3D printing offered an agile manufacturing for these components, and it was relatively cheap, 32 euros per part. Now, if they had to do this using conventional manufacturing methods, such as carbon laminates manufacturing, they would have needed to, after designing, to first build a mold and then using the mold to produce each part. Now, the mold needs machining. It's normally a complex metal part, or made with it can be made with different materials, but they estimated a cost of 600 euros per mold. So only to make 3 parts, they needed to spend 600 euros each, and in addition 90 euros to manufacture each part. Now, you can see the tremendous advantage that 3D printing has, because with no need to make molds, it offers you the possibility to really freely change the design of what you're building, and then to test it at once. So, in conclusion, we have talked about our filaments, our portfolio of filaments, and we've talked about different mechanical properties such as strength, stiffness, heat resistance, chemical resistance, and we have suggested a different use for each one of our filaments. Then we have talked about fibers, and we have talked about what are they used for, and what do they apport when they're introduced into a thermoplastic blend for 3D printing. Then we have talked about a real application of 3D printing and fiber-filled filaments, and as was the case of the components for the racing cars. And now I would like to leave you with this message. Now that we have analyzed all the mechanical properties of these filaments, now you probably realize that stronger is not always the best. Now, each filament has its own characteristic, and it's good for something. So if you want something flexible, you will need to go for TPU. If you want something that's chemical resistance, you will have to go to polypropylene, and so on. So each material has its own identity and its own ideal application. So we suggest you carefully read the technical data sheet, and I hope this presentation was of help for you. And if you have any question, please remember to send an email to info@bcn3d.com. We will be very happy to reply and to give you suggestions and to talk more about our products and our technologies. Thank you very much.